In this video, I'm going to go over some examples for how to calculate and prove the time complexity of an algorithm. I will go over 3 examples: linear search, binary search, and Euclid's greatest common divisor. Euclid's greatest common divisor is a difficult algorithm. Those of you in ECS 32B are not expected to prove the time complexity of something like this, but I thought it would be instructive to show you the process. These are the steps we are going to follow to calculate and prove the time complexity. First, from the algorithm, we will find t of n, the runtime function of the algorithm. Next, we will find the dominant term of the runtime function and call it f of n. And then we will choose the constants c and n naught and prove that the runtime function is bounded by c times f of n for all n greater than or equal to n naught. Let's go over a basic example, linear search. What is the worst case big O of this function with respect to n, where n is the length of the list? Linear search is an algorithm that checks whether or not an element is present in a list. It does this by looping through the list and checking whether or not the element is present at each index. The first step is to find the runtime function. We do this by counting the number of operations that the function performs. In the worst case scenario, the function will loop through every element in the list, perform one comparison per element, and then return. Since there are n elements and we do one comparison per element plus the last return, our runtime function is 1 times n plus 1, or just n plus 1. Now that we have the runtime function, let's find the dominant term. We know that n is the dominant term since it will grow faster than the rest of the function, so when n is large, the function t of n will be dominated by the n term. Now we will choose our constants c and n naught so that we can prove that this function is O of n. There are many valid combinations of c and n naught, but here's the approach that I use. First, I set c to be a constant greater than the constant in front of the dominant term of t of n. In this case, that constant is 1, so let's set c equal to 2. Next, I set c times f of n equal to t of n and solve for n. This gives us the value of n, where the function c times f of n overtakes t of n. C times f of n will be greater than t of n for any n greater than this n, since c times f of n grows faster than t of n. Setting the functions equal, we get 2n equals n plus 1, then we subtract n on both sides and we get n equals 1. We then set n naught equal to 1 because we know that for any n greater than or equal to 1, c times f of n is greater than or equal to t of n. Since n naught must be a positive integer, if the number we solve for happened to be a decimal, we would round up, or if it happened to be negative, we would use a positive integer instead. Finally, let's prove that this is indeed true. We have 2n is greater than or equal to n plus 1 for all n greater than or equal to 1. Subtracting n from both sides, we have n is greater than or equal to 1 for all n greater than or equal to 1, which is a true statement. Therefore, t of n is O of n and has linear runtime complexity. Let's go over another example, binary search. What is the worst case big O of this function with respect to n, where n is equal to the length of the list? Binary search is an algorithm which finds the index of an element in a sorted list. It does this by checking the middle element and comparing it to the element it is searching for. If the element is greater than the middle element, then the element, if present, must be in the right half of the list. If it is less than the middle element, then it must be in the left half of the list. This is because in a sorted list, all elements greater than some element must appear on one side of that element, and all elements less than that element must appear on the other side. Let's find t of n. There are 3 operations which occur before the while loop. Then, in each iteration of the while loop, the midpoint of the list is calculated, and then the loop will go into one of the 3 if paths. Since we are finding the worst case complexity, let's assume that the loop always goes through the first if and returns -1 at the end. Each time the loop is run, the area of the list that we are searching in is halved. This means that the loop runs log base 2 of n times, since log base 2 describes the number of times you need to half a number to get 1. This means that our runtime function will be 4 plus 3 times the log base 2 of n. Now that we have the runtime function, let's find the dominant term. 3 times log base 2 of n dominates the expression for large n values since it is the term which grows the fastest. Next, we set f of n equal to the dominant term without the constant. Now let's choose our c and our n naught. Once again, I will choose c first by setting it equal to a constant greater than the one in front of the dominant term in t of n. In this case, I will set c equal to 4. Next, we set c times f of n equal to t of n and solve for n. This gives us the point that the function c times f of n overtakes t of n, and from this we could choose a suitable value for n naught. So 4 log base 2 of n equals 4 plus 3 log base 2 of n. We can subtract 3 log base 2 of n from both sides, and we get log base 2 of n equals 4. Then, taking 2 to the power of both sides, we get n is equal to 2 to the power of 4, where n is equal to 16. From this, we will choose our n naught to be 16. And now we will prove that 4 log base 2 of n is greater than or equal to 4 plus 3 log base 2 of n for all n greater than or equal to 16. Subtracting 3 log base 2 of n from both sides, we get log base 2 of n is greater than or equal to 4, and taking 2 to the power of both sides gives us n is greater than or equal to 2 to the power of 4, or 16. And since we have n is greater than or equal to 16 for all n greater than or equal to 16, which is a true statement, t of n is O log of n, and has logarithmic time complexity. For the last example, let's look at an algorithm that is over 2,000 years old, Euclid's greatest common divisor. Computing the runtime function for this algorithm is more difficult than most of the algorithms you'll encounter in this class. However, I decided to include it because I think it would be helpful in showing you how to approach more difficult complexity problems. So what is the worst case big O of this function with respect to a or b? This function computes the greatest common divisor of two integers a and b. Let's take a look at the code. While b is greater than 0, r is equal to a mod b, a is equal to b, and b is equal to r. Then we return a. There are 3 operations in the loop and 1 operation out of the loop. However, we do not know how many times the loop is run. This function takes in 2 integers where a is supposed to be the larger of the 2 integers. If b is larger than a, then in the first iteration of the while loop, r equals a mod b. Since b is larger than a mod b is equal to a. And then you switch a and b, so essentially, if b starts out larger than a, the first iteration of the while loop will switch that. However, for this proof, we will be assuming that b is always the smaller input. To see how many times the loop is run, we need to look at what happens to b after each iteration of the loop, since the loop condition is while b is greater than 0. A mod b outputs a number between 0 and b minus 1, so we know that r is less than b, and then a is equal to b, which is greater than r, and b is equal to r. So after the iteration, b is now equal to a number that is at most b minus 1, and a is equal to b, which is greater than b minus 1. So since the new a is still greater than the new b, the next time we run through the loop, b will decrease again and the cycle will continue until b equals 0. So we know that the function will eventually terminate, but we still have no measure of how long it will take. Since b is decreased by at least 1 each iteration, the loop must run for at most b iterations. However, if we look at the value of b after each iteration, we will get b is equal to a mod b after iteration 1, b is equal to b mod a mod b after iteration 2, and b is equal to a mod b mod b mod a mod b after iteration 3. And if we write these terms down, we will see that it forms a recursive sequence where b of n is equal to b of n minus 2 mod b of n minus 1. Since the recursive sequence is defined by two previous terms, if we find the minimum value by which b decreased by after 2 iterations, we know that every pair of 2 iterations after will decrease b by at least that amount as well. After 2 iterations, b is equal to b mod a mod b, where the a's and b's are the ones from the input of the function. So what is the maximum value of b mod a mod b? We know that a mod b outputs a value between 0 and b minus 1, and we know that b mod a mod b is less than a mod b. So if a mod b is small, then b mod a mod b will also be small. We also know that if a mod b is greater than b over 2, then b mod a mod b is equal to b minus a mod b. Let's split this up into 3 cases. If a mod b is less than b over 2, then b mod a mod b must also be less than b over 2, since it is less than a mod b. If a mod b is greater than b over 2, then b mod a mod b is equal to b minus a mod b, which must be less than b over 2, since a mod b is greater than b over 2. If a mod b is equal to b over 2, then b mod a mod b must be 0, since a mod b must be an integer, and also a mod b must divide b, since a mod b is equal to b over 2. This means that after every 2 iterations, b has halved, which means after every 1 iteration, b has decreased by a factor of the square root of 2, which means that the while loop runs for at most log base square root of 2 of b times. So the runtime function is 1 plus 3 times log base square root of 2 of b. Now that we've found the runtime function, everything else is the same as the previous 2 examples. Since our runtime function is with respect to b, we are going to call it t of b instead of t of n, and we are going to replace n and n naught with b and b naught. First, we find the dominant term. In this case, it is 3 log base square root of 2 of b. Then we set f of b equal to log base square root of 2 of b. Then, we choose c to be an integer greater than the constant in front of the dominant term. In this case, I will set c to be 4. Next, we set c times f of b equal to t of b, and solve for b. From this point, I'm going to say log of b instead of log base square root of 2 of b because it's easier to say. So we have 4 log of b is equal to 1 plus 3 log of b. Subtracting 3 log of b from both sides, we get log of b equals 1. And taking the square root of 2 to the power of both sides, we get b is equal to the square root of 2. And since b naught needs to be an integer, we will round up and set b naught equal to 2. Finally, we will prove that 4 log of b is greater than or equal to 1 plus 3 log of b for all b greater than or equal to 2. Subtracting 3 log of b from both sides, we get log of b is greater than or equal to 1, and taking the square root to the power of both sides, we get b is greater than or equal to root 2 for all b greater than or equal to 2. And since 2 is greater than root 2, this is a true statement, and t of b is O log of b and has logarithmic time complexity.